Okay, how do you want to answer this first one? What do we mean by colligative properties? Anyone?
They refer to the properties that can change.
Okay. Let's go with substance. That's probably a better word. So some pure substance has its properties changed when what happens? With the addition of a solute. So you throw a solute in some pure liquid and the properties that we study as chemists change. So what effect does it have on the liquid state? Is there an easy way to say that? How about I got more liquid state? I increased the span over which the liquids or the substance is a liquid. It's got a lower melting point and it's got a higher boiling point, so it's a liquid over a larger range of temperatures. I got more liquid.
Is that true for all liquids or just water?
It's true for, it'll be true for all liquids, yeah. Colligative properties aren't subject to just water, it's just that it's almost the only thing we ever really talk about. When a salt's added to water, why does the boiling point elevate? What's going on there?
Just to break the forces between the water and
Okay, so what you have are new intermolecular forces, right? I had the partial positives and partial negatives, and now I have full-fledged pluses and full-fledged minuses. So I throw table salt into water. Now the water doesn't necessarily just have to break free of other water molecules, it also has to break free of the sodium ions and chloride ions. And so the amount of energy, the kinetic energy of that water molecule needs to be higher to actually break free. Because if I'm boiling something, it's the surface that's leaving, right? That water molecule is leaving the surface, so it's got to be moving upwards, and now it's got to be moving upwards faster to bust free of what it's being attracted to. How about that freezing point? Why does that depress? Same reason? I'll definitely say that you're going to have new intermolecular forces, but how does it differ that are stronger?
It interferes with the crystalline structure of the solid.
So I've got a nice organized crystal matrix structure, which now has been disrupted because the stronger intermolecular forces that have been added to the solid cause the molecules themselves to rearrange. All right, so calculate the final concentration of these things. When I need concentration, what are the units that I'm looking for? with what I've got up here, what am I looking for? Molarity, we okay with that? So what are the units for molarity? I need moles per liter. So I need some number that's got moles and some value that's got liters. So if I can put a mole number up top and a liter number on the bottom, I can get myself an answer with this. Okay, so how am I gonna get the liter number and the mole number? I can get the liter number pretty easily, can't I? So what we're looking for is the total number of particles in here of the moles, and then the total volume of the solution. So what's the total volume of this solution? 2.65 liters. We okay with that? So the 250 milliliters, the 400 milliliters, and the 2 liters. So I have a total volume of 2.65 liters. Great. So now what I need is to add up all the moles that are in each of those individuals and put those together. So I had 2 liters of pure water, so that has nothing to do with the molarity of the sodium chloride. And then I've got a 1.75 solution and a 1.3 solution. So 1.3 moles per liter. Moles per liter. And I've got, how much? 250. So 0.25 liters. And then I had a 1.75 mole per liter. And I had a 0.4 liters. So, got 1.3 times 0.25 and 1.75 times 0.4. And so I've got 0.325 mole, and I've got 0.7 mole. So add those guys up, I get 1.025 mole, 1.025 mole, 1.025 divided by 2.65. I got 0.38, 0.39. Does that make sense, how I did that? So I'm taking this container and this container and I'm putting them in that container. So all I really need to know is the total volume and the total number of moles, and I could figure out how many sodium chlorides are inside this container and how many sodium chlorides in this container. So when all 3 of these things go together into that container, I know how many actual sodium chlorides are in there as far as moles go. Okay with that? So quiet. Which one of these 2 things is a better electrolyte? Yep. How come that one is better?
More
3 pieces. I got a calcium with a +2 charge, and I got a chlorine with a minus charge, and I got a chlorine with a minus charge. Up here I've got a magnesium with a +2 charge, and I have a sulfate with a -2 charge, but I've only got 2 particles. So in this case I've got 3 pieces which are able to disrupt the crystal matrix structure, or 3 pieces which are able to transfer electrons, since we're talking about electrolytes. And on the bottom I've only got, I've got 2 pieces to transfer electrons. So in this case, the N is equal to 3, and in this case, the N is only equal to 2. What's the percent solution? 35 grams, 400 milliliter solution. All right, so I've got 35 grams of KCl. I'm going to divide that by 400 milliliters. So 35 divided by 400, 0.0875. Oops, that's not it. Not done yet. Times 100. So I get 8.75%, and then M over V, so a mass to volume. I guess technically it's only 9%, or it's 9%, since it's 1 sig fig. Do we have any questions about that one?
Can you explain the other one, which one is a better electrolyte, because I'm kind of confused, I don't understand why.
Okay, so when I throw something into the water and that water is able to now transfer electrons, you get electrical flow. It's because the ionic things are able to move charged particles back and forth. So when I've got water, it's just H2O molecules and there isn't a charge on it, so it isn't able, the water molecule itself isn't able to take positives and move them from one side and negatives and move them to the other side. So I need to put something in there that's charged that will actually start moving things around. So if I put the calcium chloride in there, how many trucks do I have to move the positives and negatives around? 3, because it breaks up into 3 pieces. And then the magnesium sulfate, how many things do I have to move the charges around? 2. So that's why it doesn't work as well. They're both absolutely electrolytes, and they would both allow electricity to flow, but you need less calcium chloride to get the same effect. And you would also, if you put calcium chloride into like ice, it would be 25% more effective because it's got an extra piece there. Does that make sense? Okay. How about this next one? What do we want to do? What's that VV stand for?
Volume, volume.
So what kind of substance do I have?
Liquid.
And?
The liquid.
2 liquids there. Okay, so in this case, I know I've got 3.5%, and this is 100 times, and what is the beer in this case? Is the beer the solute, or is the beer the solution? Solution, so 454 milliliters down here, and then I don't know what the volume of my alcohol is. So then I'll rearrange this, and I've got X is equal to 3.5 times 454 milliliters divided by 100, and so 3.5 times 454 divided by 100. So 15.89 milliliters, and 2, so about 16 milliliters of actual alcohol in that can of beer. Which equations did I use for the previous 2 questions? I used percent mass volume and percent volume volume. Okay, so what are we gonna do with this one here? I need to calculate out what my new freezing point is for this one. What's the freezing point temperature for this guy? So the equation is change in the temperature of the freezing is equal to NKF molarity. Alright, so it's magnesium chloride. So what's my N value? What is it? What's the formula for magnesium chloride?
MgCl2.
So what's my N?
3.
3. 1 magnesium, 2 different chlorides. So then I've got an N equal to 3. And then I give you the KF right there. The KF is just something that you would look up in a book. And so that's 1.86 degrees Celsius, and then molarity. And then I'm going to multiply by 2.5 molar. Alright, so I've got 3 times 1.86 times 2.5. So I get 13.95 degrees C. Cool. Cool. Am I done? I'm not. What's my answer? Oh yeah, I gotta convert to Fahrenheit. What do you wanna do first? I don't think we wanna convert first. We need to do one thing first, which is what? No. Subtract from 0. What did we what is 13.95? The change in the freezing point. Well, what is the freezing point of water in degrees Celsius? 0. So what's the new freezing point now that this magnesium chloride's been added? Negative 13.95. That's going to be pretty important, because if you don't do that, then this is going to look really weird. If you don't do that, then it's going to say that the new freezing point of water is like 50 degrees Fahrenheit, which is silly since it only ever goes down, never goes up. All right, so we know that this is a change in the freezing point, and which direction does the freezing point always change? It always goes down. And which direction does the boiling point always change? It always goes up. So you were just on your own to remember which way the change goes. So the new freezing point is 13.95 degrees C. And so now I need to convert that over to degrees Fahrenheit. So let's see, it's which is first? Do I add the 32? No, I multiply by 9/5, and then I add 32 to it. So negative answer times 9 divided by 5 plus 32. So 6.89 degrees Fahrenheit. Got 2 sig figs, so 6.9 degrees Fahrenheit. Does that number make sense? Does that seem reasonable, that 6.9 degrees Fahrenheit? Is that cold? Yep. 32 degrees is regular freezing. And this is well below degrees Celsius freezing, so that's well below Fahrenheit freezing. Okay.